Hi again. My sincere apologies for not being able to get through this in class this morning. The technology issues were something else, clearly. So hopefully, at least I'm able to get this up on YouTube, and you're able to watch it, and still be able to get the ideas that I want to get across, and still be able to figure out effective ways for you to ask me questions about the material without us needing to go back and forth in a live fashion. Hopefully, it'll work on Monday. But if the technology issues continue, we may just have to go to some other recording and you asking me questions after watching the recording. I'm at a loss for what else to try, as bad as that technology issues was this morning, because I even got the special magic box thing from Sprint, and clearly that did not make it any better today. So anyway, let's go ahead and talk about this Graham Schmidt material that we started before last time. All right, so let me try to go back to what I was just talking about this morning. Let me erase some things that I actually wrote so I can rewrite them. All right, so the whole idea behind the Graham-Schmidt process, again, is to try to convert a basis for the space that you're talking about into one that's orthogonal. The reason why we care about orthogonal bases and orthonormal bases, again, is because it's easy to find coordinates relative to a basis if you have an orthogonal basis to start with. So that was one of the things that we proved last time, that if you have an orthonormal basis, then the coordinates for anything that's in your vector space, for any W in your vector space, are just the inner product of that vector with each of the basis vectors. So remember when we had to do coordinates with respect to a basis, we had to put it in a matrix, we had to row reduce, and solve that system of equations. In this case, we don't even have to work that hard. If we have an inner product space, and I know that I have an orthonormal basis to start with, I can pop out the coordinates just by doing the inner product of the vector with the individual basis vectors. And again, what that allows us to do is make inner product things look more Euclidean. That's what this theorem is here that I know I didn't prove last time. But notice that if you have a basis and you want to do things like take the magnitude of W, it looks like what the magnitude of W would be in Rn. So let's go through that real quick before I go back down to talking about how we do the Graham-Schmidt process. So we know that, I'll do it with the magnitude squared, because again, it's easier to deal with the magnitude squared typically because of the fact that there's that square root in the formula. If I square it, then I don't have to worry about square roots while I'm working with it, and then I can do a square root at the end. This is the inner product of W with itself. Well, I know what the coordinates of W are with respect to that orthonormal basis. In particular, I know that W is equal to little w1 times v1, little w2 times v2, all the way out to little wn times vn. And we're going to do that inner product with itself. So I'll have that same vector here in the second component. Oops, forgot my W. And then with our properties of the inner product, we know we can do a big, long distribution of these things. Now, we get a little bit of help. I'm not going to write them all out because we get a little bit of help with these things. But the first one would be, I would take this one times this one. You would get W1 squared V1 inner product with itself. If we take the first one and the second one, we would get W1, W2, inner product V1 with V2. Now let me stop there. We have an orthonormal basis. Ortho part is the important part in what I want to emphasize here. The ortho part means all of the vectors are orthogonal to each other. That means that this inner product here is 0. So this term goes away. And notice that when I take this term now and distribute it to the rest of the sum, all of those terms are going to go away. So the only thing that's going to be left is that first term. Likewise, So I'm just going to write that down. We're going to get a bunch of zeros in there. Likewise, when we take the second one and distribute it, the first one's going to get a V2 inner product with V1. That one's going to go away. Then I get a V2 with a V2, so the second piece is going to be W2 squared inner product of V2 with itself. And then the rest of them, when I take the V2 with the rest of them and do the inner product, those are all going to be 0, because again, it's an orthonormal basis. And in particular, it's orthogonal, so you'll get a bunch of zeros there. To emphasize again for the third one, when we take the third one with the first one, we would get 0. When we take the third one with the second one, we would get 0. Third one with itself, we get the W3 squared inner product of V3 with itself. And then again, the rest would be 0. All the way down to a bunch of zeros until we get to the very, very last one and get Wn squared inner product of Vn with itself. So all we're left with, when I write all of that mess out, I wrote it out longhand just kind of illustrate what was going on, but what we're left with is W1 squared inner product of V1 with itself, W2 squared inner product of V2 with itself, all the way to Wn inner product of Vn with itself. And that only used the orthogonal piece of the basis, right? We still have that orthonormal piece of the basis. So the normal part refers to the fact that the magnitude of everything in your basis is 1. So this is 1. This is 1. This is 1. So this is going to simplify just to W1 squared plus W2 squared out to Wn squared. And then taking square roots gives us the result that we want back over here. Okay? So that's, again, the big deal about why we care about such things. If we have an orthonormal basis, if we can calculate the coordinates easily by just doing the inner product of the vector that we're interested in. And once we have the coordinates, we can calculate things like magnitudes, distances, inner products, just like we do in Euclidean spaces. That's a pretty cool result. That's what we care about in this case. All right. So hopefully that gives you a little bit more insight into why we even care about such things as inner product spaces. Okay, so back to Gram-Schmidt. Again, the idea then is to use the Gram-Schmidt process to create an orthonormal basis by doing this particular process. So again, the process involves start with your first vector, we call it V1. Our second vector that we have that's in our base is probably not orthogonal to V1. So to get a vector that is orthogonal, the first thing we do is we drop down that perpendicular and calculate the projection. So that red vector that I just drew is the projection of V2 onto V1. Now the projection, of course, is a vector that's in the same direction or the exact opposite direction as V1 is. And we typically refer to that as parallel to V1. It's a scalar multiple of V1. So to find the one that's orthogonal, this one, we'll take our V2 and we'll subtract off the projection. That'll give us the one that's on the right-hand side of that right triangle. And so this is the vector that we're going to call W2 in our process. All right, so just to write down the process again, the W1 is the V1. The W2 is we take the V2 and project V2 onto W1, which is the same as V1, but we just want to be consistent with our notation for what we're using for the basis that we're forming. All right, how do we get W3? Well, let's see if I can draw the picture again. This was in the handout, but let me try to go through the idea. All right, we've already created W1 and we've created W2. And we know that these are orthogonal to each other and they generate some subspace, whatever that happens to be, which I think in the notation or in the handout I told you, I just refer to it as an arbitrary W. Now, again, we've got some V3 out here lurking, wherever that happens to be, probably not perpendicular to everything. Okay? This is probably not, could be, I mean, we might be lucky and it might be perpendicular, but it's probably not. So again, to find something, we need to drop down a perpendicular to this subspace and figure out what this vector is. All right. So the idea, of course, is that we need to figure out what this projection is here onto W. So we refer to this as the projection of V3 onto the subspace W. And so this question mark then will be V3 minus that projection vector. That was weird. So the projection vector of V3 onto the subspace W. Let me rewrite that. That's ugly. All right, so this question mark here, which I hadn't read to start with, that question mark is V3 minus the projection of V3 onto W. And then I'm not going to go through the derivation again here, but the way that you get this projection is the same way, essentially the same way we got the projection of V2 onto W1. So when you do your projection vector, W3, it's going to be V3, and it's going to end up being minus the projection of V3 onto each of the two previously found basis vectors that are orthogonal to each other. The reason where this comes from is because basically this projection vector has to be a scale. It has to be a linear combination of these two that we already found, because this vector is in the subspace that's generated by W1 and W2. That's what's in the handout. So that's where this part comes from. And then you continue in the same fashion for the next one. If you had a W4 that you were interested in, you would do V4 minus the projection of V4 onto W1 minus the projection of V4 onto W2 minus the projection of V4 onto W3. That's how you find such things. And continue until you run out of vectors. That's the idea. We essentially went through that process in the previous example that I did on Wednesday. So let's see if we can find another one that's a little bit, it's the same idea, but let's see if we can do the same kind of concept, just using a little bit bigger numbers. So this is number 18 on page, whatever page we're talking about, 330. They use U's. I'm going to write V's. I don't know. It doesn't matter. All right. 0, 2, 1, 0. 1, negative 1, 0, 0. 1, 2, 0, negative 1. And 1, 0, 0, 1. All right. And we're going to use the Gram-Schmidt process to convert this into an ortho and normal basis. And right now we're just assuming that we are using the standard Euclidean inner product. This process can be used for any inner product space that you want, using any inner product that you want. So, but we're going to use the standard Euclidean product, inner product, for this particular example. And in particular, I want to show you a little bit about how we can do this on the calculator. All right, so to that end, so we already know that W1 is going to be 0, 2, 1, 0. All right, so let's go to your calculator. Now, also, if you're interested, and I'm going to send this in an email too, so you don't have to catch this while I'm lecturing, I have written, I'm going to tweak it a little bit, make it a little prettier, but I've actually written programs that will do inner product, magnitude of vectors, angle of between vectors, and will give you the result of the Gram-Schmidt process for the TI. Now, if you have a TI CE that's got the cable that connects directly to your computer, I can just send you the files and you can use the TI Connect to get to it. If you don't have that, but you really, really want the programs, I can just send you what the text looks like and you'd have to type them all in. But if you've got a way to connect your calculator to the computer, I can get you the programs if you're interested in them. You just have to contact me. However, even if you're not interested and want to know how to do some vector stuff on your calculator and know how to go through it on the process by hand, I want you to know how to do it by hand anyway, but let me show you how you would do this. So the first thing I would do is go into your lists. All right, oops, sorry. Let's go clear that out of there. We need to go to Stat. We're going to edit some lists here. I am going to use, I got some other data in here that I want to use for another thing that we're going to talk about later. But you can type your vectors into these lists and use these lists later for other operations if you want to store them for later. There's another thing that you can do, and since I've got data in there, I don't want to delete out because that's for a later lecture. I forgot that I had that in there. You can also convert any other letter that's on your calculator into a list. So if I go to second list and go over to ops here, if I go to the very, very bottom of the list, there's an L. If you put that L in front of any variable, doesn't matter what that variable is, it makes it a list. Now, this one didn't have the A did not have a list defined in it, but let me show you how this actually works. So when you put braces around things, so in this one, the first vector was 0, 2, 1, 0. That's a list. I put braces. So notice the braces are right above the parentheses. So I did second left parenthesis to get the left brace, and similarly for the right brace. So this is a list. If I want to keep referring back to this list, I probably want to store it into something instead of typing it in over and over and over and over again. So I'm going to store. So I hit the STO button here. Then I'm going to go to second list. I'm going to go over to the ops. I'm going to go to the bottom of my list, and I'm just hitting the up arrow. It cycles me to the bottom of the list. Put the little L in front, and then use a letter name. Doesn't matter. You've got 26 to choose from. Plus, you can actually use the theta as well. And get that for your list. Okay. Now, notice that if I go back and just want to reference that list, if I go back and do the same thing, get the little L, don't hit the enter key twice, hit alpha A. There, it's stored in there. But also notice that it knows that that's different than the number A. So you actually have to have the little L in front of it to store it, if you will, to reference it, I mean. All right. Now, how do we find our second vector? So let's put our second one in here. So let's do, the second one was 1, -1, 0, 0. I want to store that as a list in letter B. Okay. So I want to take this list. Now, sometimes it's tedious because I have to go back and get that little L all the time. But I want to take list B, and I want to subtract off, what is it? It's the projection of list B onto list A. So remember how we do that. We have to do the inner product of the A with the B, and then divide by the inner product of A with itself, and multiply it by the A. I can do all of this on the calculator. So let me show you how to do that. First, let's do the inner product of A with B. So I'll go second list, operations, oops, sorry, not operations, math. Notice there's a sum command here. Okay, so if I want the sum, what it'll do is it'll take every element that's in the list and add them together. Okay, so it doesn't mean, I hit the wrong button, clearly. It does not mean add two lists together. It means take everything that's in the list and add those things together. So that's part of your inner product, right? Adding the products together. So what do I want to add together? I want to take the A times the B. So do second list A and multiply it by list B. So when I say multiply two lists together, it does it component-wise. So if they don't have the same length, if there's not the same numbers in the lists, it'll give you an error. But if I take list A times list B, it'll take those 0 times the 1, the 2 times the -1, and so on, and make a new list. The sum command adds it together. So this is exactly the inner product of those two things. So I want to do the same thing. But I want to do that with the inner product with A itself. So I want to do a list of A. Now I think this will work. I haven't actually tried this, but I think if I do list A squared, it'll square everything in the list. So that should be multiplying A by itself. And then I want to do second list A. Because remember, I want to take this number and multiply it by A. The list, the vector. Okay, so let's see if this works. Oh, it did. Cool. All right, so this is our new vector that we want. So this is, if I go back over to what I'm writing down, our W2 is the 1, -1, 0, 0, minus, and instead of writing out the numbers, I'll write V1 dot product with V2, inner product with V2, V1, I should call this W, inner product of W with itself times W1. And that gave us 1, -1/5, 2/5, and 0. Yeah. So that gave us the second vector. I'm going to store this one as well. So let's store it as, I've already got B. Yeah, let's use C. It's fine. I didn't really need to store list B before. All right, so I have A and I have C. Our next vector was the 1, 2, 0, -1. So I'm going to be a little clever here. 1, 1, 2, 0, -1. And I'm just going to enter it so it's in the previous answer. So now I want previous answer minus the sum of the previous answer times list A divided by, and if you want to store some of these things so you don't have to type it in every single time, that's good too. List sum of list A with itself. And then again, this is times list A. All right, so just to take a break, because I just typed a lot of stuff in, this part is the dot product, the inner product of this vector that we're trying to project onto the first vector that we have. And now we need the exact same statement, except that I need list C everywhere where I see list A, because I need to project this new list onto the previous one that we just found. So this will be minus list sum previous answer times list C, and get a parenthesis in there, divided by list sum of list C squared times list C. Okay, again, just to take a second to see what we typed in. The sum of previous answer times list C is the inner product with the vector that we're working with and the last vector we just found. This is the inner product of that vector with itself and then just multiplying it by itself. So this is the projection of the vector we're working with onto the second one that we found. And I'm going to need this for later, so I might as well store it now. So let's store this as list D. So our third vector here, W3, this again is going to be the 1, 2, 0, negative 1. This is minus the projection of V3 onto W3, minus the projection, W1, minus the projection of V3 onto W2, which was 1/2, 1/2, and I forgot the other two numbers, -1, -1. Cool. All right. Almost done. One more to go. Same idea. 1, 0, 0, 1. Oops, I did that backward. 1 minus, oops, sorry, not minus yet. I want to go ahead and just get that in the previous answer so I don't have to type it in over and over again. Previous answer minus. I need essentially the same thing that I typed before. Why don't I just do that? Let's clear this out. Do second entry twice. This types in everything that we had before. I don't want this store here right now, so I'm going to delete that out. Okay. But this is exactly what we want to do. We want to take the previous answer and do the projections, which is exactly what we typed in before. So I don't have to type this in again and again. So now minus the sum of the previous answer times list D is what we want this time, because that was the one we just made. And then divide that by the sum of list D squared and then multiply that by list D. And I'm going to store that because I want to keep it for future reference. So let's put it in list E. All right. And also, you can use your typical to a fraction command that you're probably used to using and get the fractional equivalents of those decimals. So this is 4/15, 4/15, -8/15, and 4/5. Okay, so this gives us an ortho, it's not ortho, no, normal yet. So W1, W2, W3, and W4 form an orthogonal basis for R4. And you can check that they really are orthogonal. For example, if I do, say, W1 and do its inner product with W3, I get 0 times 1/2 is 0, 2 times 1/2 is 1, 1 times -1 is -1, and 0 times -1 is 0, and I add that together, I get 0. I really do get 0. To see what happens here, let's just look at this last one. We would have 2/15 when I multiply those together, 2/15, so I would have 4/15, plus another 8/15 4/15 and 8/15 is 12/15, which is 4/5 minus 4/5, which really does give you 0. So any inner product of any two of these, two distinct ones, is going to be 0. All right, so we have an orthogonal basis, but not quite orthonormal. But the orthonormal part is to divide by their magnitudes. Well, we see pretty easily that the magnitude of W1 is 1 over, not 1 over, it's actually equal to the square root of 5. W1 would be, I would take the 2 squared plus the 1 squared, and the other ones are 0, and take the square root. I can do this on the calculator as well. If I do the summation, sum of each of the other lists that we had squared, that's the inner product with itself. I get 1.2, and again, if you really want to change that to a fraction, you can. 6/5. So going back over here, the magnitude of W2 would be the square root of 6/5. You do the same thing for the other ones. Let's see if I can be a little clever and not have to retype a whole bunch of stuff. Change the C to a D. Get 2.5. So this one will be square root of 5/2. And go back. Again, be a little clever. Change the D to an E. And if I want to see it as a fraction, 16/15. So the last one here would be 4 over the square root of 15. So finally then, your orthonormal basis is going to be 1 over the square root of 5. You have to divide out by its magnitude of the 0 to 1, 0. It'll be square root of 5 over 6, and no, I do not care if you rationalize your denominator. This will be 1, negative 1/5, 2/5, 0. The next one will be square root of 2 over 5, 1/2, 1/2, negative 1, negative 1. Oops. And finally, the last one will be root 15 over 4 times 4/15, 4/15, negative 8/15, and 4/5. Tedious process, yes. Made a little bit easier by using your calculator. Made a lot easier by using the program that I wrote on the calculator. Again, if you're interested and can get it downloaded to your calculator, you're more than welcome to have it. I can send it to you. I will expect you to show me the work as you're going through these things at each step, so there is that. But if you're interested in any of the programs that I wrote for the calculator, again, just reach out. I'm more than happy to send them to you. Like I said, I wanted to go through another example all the way through because I didn't have a chance to do that the other day. So let's see here if I have anything else listed on this sheet before I go to the next one. Nope, that was the last thing I wanted to do on here. So I think I'm going to stop this video here. I will record another one for the least squares, what we were going to do today. I'm going to do that as well, but I think maybe you want to take a break and digest this one before diving into the next one. Plus, there's also another least squares one that you should watch, as well as a least squares example on YouTube as well. So you should actually, by the end of the day, you'll have 3 different least squares videos to watch. So again, I apologize for the technical difficulties this morning. It was, I'm sure, frustrating for you as it was for me. I sincerely apologize. I hope things will work out better on Monday. I really don't want to go to asynchronous. I don't personally like it. I don't think it gives you a good chance to interact with me if you need to. But if that's what we have to do, that's what we have to do. Luckily, there's only 3 weeks left to go in the semester. So anyway, I will talk to you all later. Enjoy your weekend.